Hello dear students, welcome you all. In this lecture, I am going to discuss about the application of semi-empirical mass formula. The application is to find out the mass of most stable isobar by using semi-empirical mass formula, right? So here in this lecture, I am going to drive a relation and equation that will tell us about the mass of most stable isobar. And for that, I am going to take the help of semi-empirical mass formula. First of all, we have to understand what are the isobars. We know very well that isobars are those nuclei which have same mass number, but they have either different number of protons or different number of neutrons, but their mass number is same. I can give you an example, very common example. 7 nitrogen 14 and you have 6 carbon 14, right? You can see mass number is A is 14 in both the cases, but for first we have a proton 7 and for the second we have proton 6, neutron 7, neutron 8. So this is the case. I am showing you one more example. It is related to the mass number A is equal to 40. So for A is equal to 40, I am taking the case of 3 isobars. Even more isobars are possible at this mass number, but the prominent ones are 18 argon 40, 19 potassium 40 and 20 calcium 40. So you can see here, now we have 3 different nuclei which have a same mass number, what different atomic numbers, right? They have different number of either neutrons or protons from one another, but the mass is constant. Now how we can tell that which of these 3 will be the most stable? 1, 2 and 3. Which of these 3 nuclei is the most stable, or which of these 2 nuclei is most stable, right? So I must have a formula that can tell me that in some cases in periodic table there are some mass numbers at which we can have around 10 isobars, right? Now we must know which of these isobars is most stable. So for that I am going to taking the help of a semi-empirical mass formula, right? We know very well that the semi-empirical mass formula tell us about the mass of atomic nucleus, MaZ, right? And it is written as mass of proton into Z plus mass of neutron into A minus Z, right? Minus binding energy terms, they are I am ignoring C square here for convenience. So it is a volume energy term into A minus surface energy term into A power 2 by 3 minus Coulomb energy term Z into Z minus 1 divided by A power 1 by 3 minus symmetry energy term into A minus 2Z whole square divided by A and plus minus comma 0 delta. I am writing this term for the pairing energy term that we know very well that is equal to A pairing divided by A power 3 by 2. So I am writing it plus minus delta, or it can be 0. We know very well that it can have 3 different possibilities depending upon whether the nucleus is even odd or odd even, right? Now in this equation I am going to replace this Z into Z minus 1. When Z is large, we can ignore 1. So in that case, it will become Z square, right? So I am writing here Z square. And I am also taking the different terms which are common inside the bracket, and I am separating all these terms actually. Now I am rearranging this equation. You can see here, this equation will become mass of neutron multiplied by Z minus A B plus A. Let first of all expand all the brackets, then the things will become very clear. So mass of proton into Z plus mass of neutron into A minus mass of neutron into Z minus AV into A, right, minus AS into A power 2 by 3. Then now it is minus, so it will become plus, right. Then again we will have plus A Coulomb energy Z square divided by A power 1 by 3 plus O symmetry energy into A minus 2Z whole square divided by A, and then again plus minus 0 delta, right. So this is now the expansion of the different terms. So now what I am doing, I am taking the same terms inside the bracket and taking some term outside the bracket. So MAZ, that will give me mass of neutron contain A, you can see here. Similarly this one contain only A, right. Similarly this one I can take A outside, right, and here I have to expand this term also. So I am expanding this term A symmetry into A square plus 4Z square minus 4AZ. I took the square divided by A. So when I will do it, I will get, when I will divide it by A symmetry into A square by A, right, plus 4Z square upon A minus A cancelled 4Z, right. So then further I will get A symmetry A plus 4Z square upon A symmetry minus 4Z A symmetry. So this is now the expansion of this term. So this is now the final term that I have to take into consideration. So now let's separate the like terms. Then I will get, first of all I am separating the terms that contain A. So it will give me M N minus A B. This is the first one, this is the second one, and then I have A symmetry, A surface, that is plus A surface energy divided by A power 1 by 3. When I will take A common, it will become this, then plus A symmetry. Now this is the and A common, right. You can see here in this expansion, this one, this term, and this term, they are taken as inside the bracket and A is common. Then I have a plus in next to it, plus now I am taking Z common, Z terms. So I am getting MP mass of proton, right, first term. Then the second term, that is minus mass of neutron, so minus M N, Z is common. Then the other terms that contain this one, minus 4, and we have A symmetry, right, and then this one 4Z square, right, upon A, but it is Z square, so I am not taking it, I am taking only Z common. So no, Now it is enough. We have three terms, right? Mass of proton minus mass of neutron minus 4 a symmetry from here, right? So these terms, then after plus. Now I am taking z square common. For z square, this one is the first term, 4a symmetry divided by a plus this one, this term is left, this one, a Coulomb energy divided by a power 1 by 3 plus minus delta and 0. Now this is the required expression that I got after separating different terms. You can see here I went to this up to this term, right, and then I use this term for this one, right. So I took all the terms inside the bracket which have some common factor. So I separated them as the term containing a, z and z square. Now I can modify this. So then in that case it will become mn minus ab, right, plus as power 1 by 3, right, plus a symmetry a plus z into minus 4 a symmetry minus m n bracket plus it will become minus mass of proton. I took it in this way because we know very well that the mass of neutron is higher than mass of proton, right. Then this bracket, then plus z square bracket 4 a symmetry divided by a plus a Coulomb energy divided by a power 1 by 3 plus minus delta 0. Now this is the required expansion. So now in this expansion I am going to substitute. I am considering or taking this term as a, this term as b, and this term as c. So what I got? I got m a z, that is equal to a into a plus v into z plus c into z square plus minus delta 0. Now this is the equation that I got after putting a is equal to this one, the term inside the bracket, v is equal to this one, and c is equal to this one. So it is the required equation. Then that this is equation number 2 and it was equation number 1, right. Now you know very well I started from this semi-empirical mass formula. Then what I did, I took z square in place of z into z minus 1. Then I expanded the brackets, separated the like terms, and then I arrived at this result. Now this is the equation that tells us about the mass of a nucleus. Now we know very well that this mass depend upon a and z. So if I want to find the mass of most stable isobar, right? So for the mass of most stable isobar, right? Mass of we are actually saying the mass of most stable isobar, but in actual we are looking at the atomic number of the most stable isobar. It should be said in that way, because mass is fixed. We are just looking at the number, atomic number, right? That which one, if I have two choices, then which of these is stable, right? Out of these three, which is the most stable one? So we are actually looking at the atomic number, right, Z, but we are calling it as the mass of most stable isobar because we are looking at the most stable isobar. So here, if I want to find the mass of most stable isobar, then I have to apply the condition of maxima on this equation number 2, and the condition is curly m upon curly z, right, at constant a. When a is constant, it should be equal to 0 when z is equal to z naught, right? This is the condition. Means a is constant, a is fixed, and I am taking the differential of this equation with respect to z. right? So when I apply it here, what I will get? Now considering that A is constant, so first term derivative becomes 0. Second term I will get B, and for the third term it is 2C Z naught, right? That is equal to 0, and the derivative of this is also equal to 0, right? Because this term does not contain Z, and we know very well plus minus delta. You can see here, I think I have erased it. This term was plus minus A pairing energy upon A power 3 by 4. So it does not contain Z anywhere. So obviously the differentiation will be 0. So I got this one. So from here, Z naught is equal to minus B upon 2C. So now I am putting the value of B and C. So I will get, what is V? B is this one, right? Minus 4. I am putting all these values, but minus is already there. So it will become plus. So first of all, let's put minus 4A symmetry minus, minus bracket mass of neutron minus mass of proton divided by 2C. 2 into C means, you can see here, 4 symmetry upon, you can see 4A symmetry upon A plus A Coulomb energy upon A power 1 by 3. This is the C. So I put here. So now in the next step, negative sign will be taken inside. So I will get Z naught is equal to 4A symmetry plus mass of neutron minus mass of proton divided by 2 times 4A symmetry upon A plus A Coulomb upon A power 1 by 3. So this is the required condition for the most stable isobar, right? This is the value of Z naught. So this is equation number 3. I think yes, 1, 2, 3. This is the required condition that we were looking at. So if I have the value of A, then I can tell by putting the value of A symmetry constant, mass of neutron, mass of proton on A Coulomb, I can tell that which will be the most stable isobar. I mean, I can tell the value of Z, right? Here in this expression, we know very well mass of neutron is nearly same as mass of proton. So there is no need to take this term into consideration because it is the difference of 2. So if they are nearly equal, that will become 0. So even we can ignore it. So in that case, I will be simply left with this expression, 4 times symmetry energy, right? This is now 4 times A symmetry energy, right? And you will get cancelled. So you will get 2 times. So now this is the modified formula, right? So if I put the value of A and the value of these constants, I can find out the value of Z naught. And this is the required condition for a most stable mass of a most stable isobar, right? By using semi-empirical mass formula. Now I am taking the case of one numerical problem. So I am taking the example here. You are given A is equal to 80 and you are asked to identify the most stable isobar for this given mass number. Now A is 80, right? So if we look at the periodic table, then you can see here bromine 79 point, krypton, cesium, rubidium, right? Rubidium have 84 actually, but it can have isotopes. So 78, 79, 84. Now these are in the neighborhood of this bromine, right, and selenium. Now we have to identify that which of these isobars will be the most stable, right? So for that, now let's make the calculations. So I'm going to put the value of A symmetry, that is equal to, we know very well, 19 mega electron volt. Coulomb energy term value 0.60 mega electron volt, right? And A is given, so Z is equal to 2 into 19 divided by 4 into 19 divided by A, 80 plus 0.60 divided by 80 power 1 by 3, right? So it becomes 38 in the numerator divided by, now it is 19 by 20. So 19 by 20, when I calculated it, is 0.95 plus, now the value of 80 power 1 by 3 is nearly equal to 4.24. So when I will simplify it, I will take 0.60 divided by 4.24, then I will get 0.14. So when I simplify it further, I get 38 upon 1.09 approximately. So when I further simplify it, I will get Z is equal to 34.86, right? So what is 34.86? Now it is more than 34, but it is very close to 35. So we can say 35 is the most stable. So 35. So look at the periodic table again. So you can see here 35 is for a bromine, right? So bromine, this isotope of bromine that will have mass number 40 is the most stable isobar for this given mass number 80, right? Although there can be other isobars for A is equal to 80, but this is the most stable. So this is the way of calculating the most stable isobar by simply utilizing this equation number 3, right? So we can calculate any most stable isobar by putting the value of A asymmetry energy and A Coulomb energy, right? So this is all about it. So thank you very much.